Hi, this is Adrian from Live to Learn Academy. Welcome to our lesson 3.2, Characteristics of Polynomial Functions. So this is taken directly from the Nelson Advanced Functions textbook. If you are you're a student in Ontario and you're looking to get tutoring, feel free to click the link in our description. That will take you to our website. You can fill out the form and our team would love to get in touch with you to help you throughout this course. But without further ado, let's get straight into it. So in the previous lesson, 3.1, we talked about what is a polynomial expression and what is not. In this lesson, we're going to be talking about certain characteristics of polynomial functions that you need to know. So these are general characteristics, and as we go through chapter 3, we're going to expand more and more upon these characteristics. So this lesson is a general overview. So I put some things here: degree, leading coefficient, number of turning points, and end behaviors. So let's first start off with what is the degree of the function. So if the question asks what's the degree of the function, how do we find that? If I had an example like this, this we can tell is a polynomial function. When it asks what is the degree of the function, it's basically asking what is the highest exponent in this function. So if you look at this function, the highest exponent would be the x5 exponent. So this function would be a degree 5 function or a fifth degree function. If the question said 3x squared plus 2x plus 5, then the question would be a degree 2 function or a second degree function. So it always matters on what the highest exponent is. That's what the degree is. Okay? The next thing we got to know is what is the leading coefficient. So the leading coefficient basically means based off the degree, so the highest degree, what is the coefficient of that degree? So looking back at our previous example, 3x5 plus 3x cubed plus 2x plus 5, we know that the degree is 5 because it's a fifth degree, but the leading coefficient would be 3. So in short, the leading coefficient is the coefficient of the highest degree. The highest degree term. So the coefficient of the highest degree term is the leading coefficient. The next thing we need to know are what are the number of turning points. So a turning point basically means when you have a function can look, a polynomial function kind of looks a lot like this, like a squiggly line almost. This function has different turning points. If you can look, 1, 2, 3, 4, 5 turning points. So graphically, you can find the turning points by literally just counting them out just as I did right here. And it's pretty straightforward because it's talking about the number of turning points. It's literally in the word, turning point. When does the graph turn? But what if we didn't have the graph? How would we find the number of turning points? The number of turning points is also equal to the degree minus 1. So whatever the degree of the function is, that minus 1 will be the number of turning points. So for example, if it's a fifth degree function, it will be fifth degree minus 1, which would mean 4 turning points. So number of turning points is the degree minus 1. So this is how we can algebraically determine the number of turning points. And graphically, we can just look at the graph and find out how many times this graph turns. Okay, moving on. End behaviors. So certain functions, they can look many different ways, okay? So end behaviors, you can have functions that look like this. So this is two types of functions, right? This would be a positive even function, and this would be a negative even function because it's in the negative axis. Sorry, negative even degree, positive even degree, and a negative even degree. These have different end behaviors. So the end behaviors are basically the behaviors around the ends of the function. So I'm basically trying to find out what are the behaviors of these n's. So how do I do that? What I would say for this one is as x approaches infinity, so as x approaches infinity, y approaches positive infinity. So as x approaches infinity, y approaches positive infinity. And if you look over here, as x approaches negative infinity, y approaches positive infinity. Now that holds true for a positive even degree function. But what about a negative even degree? It's a little bit different. As x approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches negative infinity. So these are the n behaviors, the behaviors around the n's, right? For a positive even degree function that goes from quadrant 2 to quadrant 1, and a negative degree function that goes from quadrant 3 to quadrant 4. So I can just write over here, this is going from quadrant 2 to quadrant 1, this is going from quadrant 3 to quadrant 4. Now, just as we have positive even degrees and negative even degrees, we also have, and I want to put this over here, we also have odd and even, odd functions, positive odd degrees and positive negative odd degrees. So let's look at how that looks like. A positive odd degree would go from these two quadrants. So this is called a positive odd degree. And this positive odd degree goes from quadrant 3 to quadrant 1. Right? Now, what are the n behaviors for this guy? Well, as x approaches infinity, y approaches infinity. But as x approaches negative infinity, y approaches negative infinity. So notice how it's a little flipped. So the n behaviors are going to change depending on if it's positive even degree, negative even degree, positive odd degree, and now negative odd degree. So let's look at negative odd degree. What does that look like? Negative odd degree goes from this quadrant to this quadrant. So negative odd. I'll actually put it over on this side. A negative odd degree function. And we know negative odd degree functions go from quadrant 2 to quadrant 4. So if we look at this one, as x approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches infinity. So with n behaviors, it's really important to determine what degree it is, if it's positive or negative, and if it's an even or an odd degree function. And remember, degree comes from what is the highest degree of the function. So if we don't know what degree it is, then we're going to completely mess up the n behaviors, which is why all of these things, all of these characteristics, they all tie into each other. Okay, let's move on to the next thing. Absolute max and mins versus local max and mins. If you were given a function, I just want to kind of explain this because a lot of people mess this up, but it's actually very, very simple. So if I have a function that looks like this, okay? Even actually, I'll make it like this. Okay, so let's look at this function. An absolute max and min refers to the absolute, meaning there is no point above this point. That's what the absolute max and min means. Or the absolute min would mean there is absolutely no point below this minimum. So if you look at this, in this function we have two minimums. We have this one and we have this one. And we actually have this one as well. 3 minimums. But which one is the absolute minimum? Which is the actual lowest point? This one. This one would be the absolute minimum. But these ones, because they're still minimums, but they're not the absolute minimums, these are actually local minimums. Okay? Now notice this function as well. we have maxes as well. This is a max and this is a max. These two are actually going to be local maxes. And the reason why is because of these two arrows, we know that this function is going to go on forever and ever and ever up. It's just going to go on forever and ever and ever up. So in this specific example, there actually isn't a absolute max. There are local maxes, but there isn't any absolute max because it goes on to infinity. But when we're talking about the minimum, there's local minimums, there's two local minimums, and one absolute minimum. So it's very straightforward, right? Absolute max and min, you're talking about the total function. What is the highest, absolute highest point and the absolute lowest point? Local max and minimums refer to within the function, are there different peaks and different valleys, right? The peaks would be the maxes and the valleys would be the minimums. Okay, cool. Let's go on to the next type of function, even and odd functions. Okay, even degree functions and odd degree functions are different from even functions and odd functions. So this is an important distinction. Even functions and even degree don't necessarily mean the same thing. Okay, this is very, very important because here we were talking about, in the end behaviors, we were talking about even degree and odd degree functions, which are these. But in this part, we're talking about even functions and odd functions, okay? So what is an even function graphically? An even function is a function that has symmetry in the y-axis. So if you look at this y-axis right here on this graph, if I take the right side, this function, and I literally fold the paper in half, it's going to appear as this function. So this is an even function because they're literally symmetrical across the y-axis. Now, an odd function is a little bit different. An odd function has rotational symmetry around the origin. So some people call it rotational symmetry. Some people call it, another word for it you might see in textbooks is called point symmetry. I'm just going to write that here so you guys have it. So it's point symmetry along this origin. So some people look at it two different ways. Some people say, okay, I take this side of the function and I kind of rotate it 180 degrees, and I'll end up with this side of the function, which is here. And if I'm rotating it almost like a windmill, I'm rotating it around this, this point, which is the origin. If I'm rotating it around the origin, then this is a point symmetry, which is an odd function. So some people look at it like that. Another way you can also look at it is you can call it a point symmetry or you can call it a double flip. And a double flip means I take the pink graph and I reflect it over the y-axis, and then I take the brown graph and I reflect it over the x-axis. So a double flip. I reflect it over the y and then I reflect it over the x. So you can call it a double flip, you can call it a point symmetry, you can call it a rotational symmetry. They all mean the same thing. But the key thing in this one is it's around the origin. Okay? If you're not able to flip it around the origin, then it doesn't work. Okay? And this is what brings me to the third type, neither. Okay? A lot of people mess this up, and I want you guys to be, I want to be very, very clear with this. You can have even functions and you can have odd functions. But just because something isn't even doesn't mean it's odd. And just because something isn't odd doesn't mean it's automatically even. You can actually have a function that is neither even or odd. And that's why this graph is perfect. If I look at this graph, if I take this part and I reflect it over the y-axis, it should be here. But it's not. It's actually here. Which means that this is not reflective over the y-axis, so therefore it can't be an even function. Or if I take this graph and I rotate it across the point symmetry, I rotate it across the origin, I'm not going to get the other function. So it's not a point symmetry or not, it's not a double flip, or it's not a rotational symmetry. So in this case, yeah, we have a polynomial function. Yeah, it's a negative even degree, right? This is a negative even degree function, right? Because of the negative even degree. but it's not a even function because it doesn't have that symmetry over the y-axis. So this is something that, is very easy to mess up. And I think, if you have trouble with this, really refer back to these notes and this chart, because it shows that a function could be even, a function could be odd, but at the same time, a function could also be neither. So how do we algebraically determine this if it's even or odd? So there are two formulas you want to know. The first one is where it is even. So even functions are reflective over the y-axis. So if we have a reflection over the y-axis, that should be equal to the regular function, therefore it's even. An odd function, however, is a double flip. It's a reflection over the x-axis and a reflection over the y-axis. So this would be an odd function. So sometimes they may give you an equation and they may say, okay, is this even or odd? So for example, we can do an example right now. They can say, they'll give us a function, let's say f at x, and I'm just going to make this really easy, x squared plus 2x plus 5. And they'll say, okay, is this function even, odd, or neither? And you will get this on a test, okay? Sometimes you may have to look at it graphically. They may give you the graphs and then ask you if it's even, odd, or neither. Or sometimes they'll say algebraically, is it even, odd, or neither? So what I would do first is I always get the f at negative x, right? Because that's the one that's for both functions. So I'll go f at negative x, and I'll actually plug it in. So negative x squared plus 2 times negative x plus 5. Negative x squared is x squared minus 2x plus 5. And then I'll compare this f at negative x. I'll compare this to my original function. And I'll ask myself, are these the same? Are they the same, yes or no? So as you can tell, these are not the same. Therefore, we know it's not even. Now some people might just say, oh, it has to be odd. No, we actually have to check if it's odd now. So how do we check if it's odd? We actually have to find what is negative f at x. So negative f at x is negative x squared plus 2x plus 5. And then I have to actually expand it out. Negative x squared minus 2x minus 5. And I end up with this. And I'm comparing this to f at negative x, which is this. Are these two the same? No, they're not the same. Therefore, it's not odd. If it's not even and it's not odd, therefore it is neither. And that's your answer. So this is how we kind of check if it's even or if it's odd. If I got the first one to be correct, let's say I got these two to be correct, then I would just call it a day and say, hey, it's even. And if they weren't correct and I got these two to be correct, I would call it a day and say, yeah, it's odd. But because both of them were a no-go, I know it is neither. Well, I hope you guys enjoyed this lesson. I hope this really clarifies a lot of things for you guys when it comes to characteristics of polynomial functions. This, I would say, is a very, very important lesson for your test. If you're somebody who needs tutoring, feel free to click the link in our description. We'd love to help you out. If you found this video helpful, please like, subscribe, comment, show love, as it really helps the channel grow. We're just here to help Ontario students. So yeah, thank you for the support thus far, and I'll see you guys in the next video.